Hashimoto.
I'm Jacob Landsiedel, and this lab is guest starring Braden Smith.
And this is the Wednesday night lab 6 to 10 Gaussian beam imaging system. So here we explain our capillarian beam expander. Here's the initial waste from the Uni laser, our two lenses that make up our capillarian imaging system, our waste after the beam expander, and our waste after it's focused down again. So what we want is waste 3 to be 1/10 the original waste. So that'll be 0.04 millimeters. And to solve for our focal length of our collimating lens, we start with this equation. This tells us the waste before and after a lens with a certain focal length. So we solve for waste 2, and we see that it is 1.007 millimeters. So then we go to this equation, which is used for the beam expander. You have the waste after and the waste initial, focal length 2 and focal length of your objective. And solving for your focal length of the objective and plugging in values for waste 1 and 2, we get that the focal length must be 119.05 millimeters. And then down here, solving for the F number, which is F over D, we see that it is 5.9, and that gives us a numerical aperture of about 0.01.
So we had solved for the focal length of the objective and the collimating lens in the ideal setup, but in this lab we had very limited supplies. We were only given a 300 millimeter focal length collimating lens. We then determined with that we could solve for the focal length needed in the objective, which we found out was not going to happen with the objective lens we had. So we determined the objective lens based on the closest numerical aperture, and we found that the Newport M20X has a 0.4 numerical aperture, very close to the collimating lens. It has a 9 millimeter focal length, which gives us a beam expansion ratio of 33.3, allowing our final beam waste to be less than 1/10 of the original beam waste.
In this experiment, the Hemi laser will pass through the spatial filter, be collimated by the 300 millimeter lens, and be imaged by the 200 millimeter lens.
When we were choosing our pinhole, we used this equation, d opt equals lambda f objective over w naught. We used 633 nanometers and f objective of 9 millimeters. And our original waste was measured in our last lab to be 0.4 millimeters. So plugging those in, it gave us a d-opt of 14.2 microns. But since we didn't want to lose any optical power, we had to use the 25 micron because the only other one available was a 10 micron.
We use the pinhole in the spatial filter to clean the incoming Gaussian beam. It's very dirty here. When we pass it through the objective lens, it takes the Fourier transform, pushing all the noise to the annulus, and then the pinhole will block out all the noise here, allowing just the clean Gaussian beam to pass through.
This image shows the Hemi laser passing through the spatial filter, which consists of a 9 millimeter focal length objective lens and a 25 micron pinhole, which will clean the incoming Gaussian beam. And here we have just a side view of the capillarian beam expander itself.
So to align the spatial filter, we took the laser, aligned it to the rail, and we aligned the objective lens to the laser from the last lab's process. We then, because we know this objective lens is a 9 millimeter focal length with a 0.4 numerical aperture, we selected a 25 micron pinhole, and we aligned this spatial filter by first putting this pinhole on the far side of the focus point, and we adjust the X and the Y translation, and then slowly move into Z. And we'll do the one axis like Y first, then X to maximize the output, and then we'll move the Z in closer, and we'll continue to do that until we clean up the beam. And our focused beam, or not focused, but our cleaned beam should look something like this once it passes through the spatial filter.
Insert a wedge shear plate after the collimating lens to check the collimation of the output beam.
After we collimated the beam using the 300 millimeter focal length lens, you can see that the sensitivity of the larger shear plate is greater as you move the Z position of the lens.
So you see the shear plate here, and as the laser beam goes into it, part of it is transmitted through it, and part of it is reflected by the mirror up to the top. And this is what we see here. This is the top-down view, and if you see that the laser beam comes in and the fringes are parallel with the laser beam, that means it's collimated. If the fringes are tilted right or left, that means it's converging or diverging. And if the fringes are wiggly, then they have significant aberrations.